Good afternoon. So welcome back in the studio. Now is next talk is a pre-recorded talk of William Alek, and he will be speaking about the replication of Tom Bearden's scalar wave technology. So enjoy his talk. Thank you.
Okay, my timeline. Okay, back in 1977, while attending IIT in Chicago, it's an engineering school or university, I was given a vision of my future. And in this vision, I was constructing an anti-gravity craft. And it's the most profound, astounding thing I think I ever saw. And it was just amazing. It was a craft, a disc craft. And I constructed this craft. And I had no idea at the time how it worked or exactly what I was doing. But in this vision, there it was. Okay, so let's fast forward here 20 years, 1979. And I went to this conference in 1997. And I attended, the speaker was Tom Bearden, and he was speaking about free energy and anti-gravity. And at the time I said, oh my God, it's starting to come together. And, with this technology. And so Tom was speaking about this free energy and anti-gravity technology, which I thought was rather extraordinary. So I went to the conference and was just completely blown away by it because Tom pointed out a flaw he discovered in electromagnetics. Okay, and we'll get into that flaw here in a moment. So now in 2022 and the present day here, I began lecturing about Tom Bearden's technology and replicating it and showing people, exactly what's going on here. So we'll go on to the next slide here. Now, Tom Bearden is noted for some quotes. And the first quote he mentioned, and this was during the conference, is that all matter is made of trapped electromagnetic energy, which I thought was rather interesting. And the second thing he mentioned was that the dimension of time, that we can't see time, but we know time exists because of spatial displacement. Okay. Next slide. Electric force versus the gravitational force. And I put this slide in here to show people out there the huge difference between the electric force and the gravitational force here. And it's absolutely enormous. Okay, the electric force, when you compare it with gravity. Gravity is as we know, is an extremely weak force. And so, and when you contrast that with the electric force, we see that we have this power of 10 to the 42nd power, but it's not zero. Okay, I want to emphasize that point. It's not zero. And this is what I caught, this is what I think caught the early mathematicians and the early physicists, was that the electric force is so enormous compared with the gravitational force that, well, we can set it equal to zero. But I think that's where the error occurred in electromagnetics and gravity. That's where the error occurred. Okay, so let's take a deeper look into this. What is the electric field, the magnetic field, and the scalar field, or gravity, okay? And scalar just means that whether it's a mass or time, it's all around us, okay? Whereas the electric and the magnetic field are considered as vectors, okay? Powerful force vectors. And then when we look at the scalar field as being all around us, that would be considered a longitudinal field, okay? And it can be either directed towards matter or emitted from matter as a change in time. Okay, I kind of think of gravity and time as almost the same thing. Because when you go into the gravity field, you measure a certain rate of time. But let's say you're sitting in orbit around the Earth, you know, away from the gravity field, you're going to have a different time. You know, clocks are going to tick at a different rate. Okay. Einstein. Okay, Einstein tried to unify the field, okay, between electromagnetism and gravity, but he failed at it. He couldn't find the connection between the two. And so he spent the rest of his life trying to make this connection with the scalar field. Of course, he failed at it. He couldn't figure it out. And so his unified field theory was, of course, a complete failure. Okay. Modern science discovered this connection, and we call it scalar waves. Okay, and this is what we're working on here: the scalar wave theory and practical applications of this technology, because it's mostly, you know, when you speak to physicists today, they either have one or two that they don't have a clue, or it's mainly theoretical. So if you look at general relativity, for example, I mean, yes, you can apply it, but it's mainly a theoretical equation, but you can't apply it to electromagnetics, as far as I know. So the next slide here, Tom Bearden's scalar waves. Okay, what exactly is he talking about? Well, what Tom spoke about in his lectures was, of course, an anti-gravitational wave, which has the properties of being time reversed and longitudinal. Okay, I want to emphasize that it was time reversed and longitudinal. This is the anti-gravitational effect, and that's what we observe with these devices. So if you take your so-called magical device that really works, you put it on a professor's desk, most likely they're not going to have a clue how this works, because it's not in their mathematics. You know, it's not the way that they were educated. Okay. Next slide. How to produce scalar waves. And of course, a number of researchers out there actually did this, okay, in their technology. And we'll get into that later on in the lecture here, okay? So what we have is a cross product of two electric charges. And these charges are set up to oscillate, okay, to converge and then to diverge. So you have this resonant type action occurring here. And that's where the scalar term appears. And of course, this is what Tom spoke about. And these vectors, okay, for these electric charge must be equal and opposite of each other, okay? And what does that produce? Well, that produces something called a zero vector, okay? Equal and opposite charges set up to oscillate produces what's called a zero vector. And Tom spoke about this as well. The next slide. Okay, two types of scalar waves are produced simultaneously here. Okay, what we see on the oscilloscope is a time-reversed EM transverse wave function. Okay, and that's what we see in our various technologies here. We see this time-reversed electromagnetic transverse wave function. The second scalar wave we see is a time-reversed gravity wave, okay? And in this case, since it's time-reversed, we would call that an anti-gravitational wave. And that's what Tom spoke about as well. Okay, time-reversed gravity, or an anti-gravitational wave, or a longitudinal wave. And that you cannot see on your oscilloscope, but you can measure it. Okay, if you hook up your device and put it on a balance beam, you find out that this device loses weight. And one of these devices, built by Floyd Sweet and his device, produced an anti-gravitational wave of up to 90% weight loss in his device. Okay, just by setting up these opposing magnetic fields. And we'll get into that a little later here too as well. So just to recap this slide, I just want to emphasize that Tom spoke about two different types of scalar waves. Okay, this time-reversed EM transverse wave and the time-reversed gravity wave. Okay, now this is the mathematics that Tom spoke about. Okay, you'll find this in some of his slides where he details the main issue here. Okay, the failure of mainstream science. And this was brought about by Oliver Heaviside, who took the original Maxwell equations, which I believe were like 20 equations written in a quaternion form. And so Oliver decided to simplify these equations. And by simplifying it, he threw out the scalar component. Okay, so what you end up with is this cross product of two electric charges producing a zero vector. Okay, and that zero vector is empty. Okay, and so this is really the crux of what Tom was speaking about. Okay, was this failure in mainstream science. Because if you look at the original Maxwell equations, he has the scalar component built into his equations. So when you look at all the mathematics here and say that with the scalar entity, you're using a sine function. Okay, so what you end up is a sine squared term. And that's very important, the sine squared term, because that's what we see on the oscilloscope, is the sine squared term. Okay, and then his zero vector becomes what's called a vacuum engine. So the zero vector actually has substance in Maxwell's original equations. And this is where the anti-gravitational longitudinal wave emerges from. So the device, you not only see the scalar wave electromagnetic term, but you also observe a weight loss in the device that's producing the scalar wave. And of course, the device must be operated in resonance to see this phenomena occur. And we'll get into that a little later here too as well. So just to emphasize that the scalar term, the sine squared term, is very important. And that's what you do not have in the vector solution that Oliver Heaviside presented and what we have today. So again, you take your device, you put it on a professor's desk, he's not going to have a clue how this works because the mathematics is not there. It's there in the original equations, but it's not there in any modern mainstream science. Okay, so this is what Oliver Heaviside did. I mean, he simplified Maxwell's equations. He did this back in the 1880s, okay? And a quotation here from Oliver Heaviside is that referring to the scalar component, why he took that out, he says that the mystical side of this equation should be murdered from the theory, okay? Because for all practical purposes, it's 0. And then Tom Bearden came along here and discovered this flaw and says that, well, Oliver Heaviside threw the baby out with the bathwater here. And then my quotation, this is the main reason why we don't have Star Trek today. We should have warp drive. We should have anti-gravity. It's built into the mathematics, but the original mathematics, not in the Oliver Heaviside. It's been thrown out. Next slide. How do you determine resonance in these type of circuits? Okay. Well, it's a capacitor-inductor combination here. So if we look at the output of these devices, we see that there's a convergence occurring with the magnetomotive forces, okay? And this is what's producing the scalar wave in our device. And so at resonance, we have minimum current in our device. It's operating at the minimum current level. And that current could go almost to 0. And this is why your efficiency goes way up in these type of devices, because your minimum operating current at resonance approaches 0, okay? So when you calculate the efficiency between your input and output, that efficiency can go into the billions if you have your coils configured almost perfectly. And this is what Stanley Myers did in his device, what Floyd Sweeten did in his device. He was able to tune the output coils such that the minimum input current can approach 0. And so your what we generally call COP, your coefficient of performance for the device, can be in the millions. Your efficiency level could be in the millions. So that means that the limit of 100% efficiency is no longer true in these type of devices. Your efficiency can go way above 100%, okay? All because of this minimum input current approaches 0. All right, so what do these resonators look like? Well, here's an example. This is my split flux, what I call the split flux transformer. And so you have an input and then 2 output coils. And this is what sets up your convergence in these devices. And so the output is driving a capacitor. And of course, there's going to be a load resistor on the output. So what you end up with is what Tom calls a pumped phase conjugate mirror on this device, or a PCM. And then I ended up filing a patent on this type of device configuration here back in 2020. And Bearden lectured on this subject quite a bit in the 1990s. So again, what we're doing here is setting up a magnetomotive convergence, okay, the 0 vector. And that's driving this capacitor and resistive load output of this device. So this is a very typical configuration. And you'll see this configuration on many of these devices, okay, that I'm about to present here. Okay, PCM resonators, what are we talking about here? And he says, okay, well, the output is time reversed, transverse electromagnetic wave. And that's the sine squared term that we see on the output of the device. The output becomes more efficient. When it's time reversed, the output becomes more efficient, and efficiencies can exceed 100%, as I mentioned before. You can approach 1,000,000%, okay, with these type of devices. And the device runs cold. They don't run hot they run cold. And that's how you know you're running this time reversed situation here. And then the gravitational component that's being emitted from this technology is time reversed as well, okay? So it's emitting an anti-gravitational effect here from the device. And so the weight can either become negative or less than zero is what you can observe for this, and it becomes anti-gravitational. So it's quite amazing here. So it affects the mass acceleration effect, okay, with this technology. Examples of PCM resonators. You know, my split flux transformer is one example. Nikola Tesla and his magnifying transmitter had the same type of coil configuration. We also see that in Stanley Meyer's water car. And we also see that in metamaterial resonators as well, okay, is that it sets up a convergence of the magnetomotive forces, okay, inside the materials. All right, so here's an example of what I'm talking about here with the split flux transformer. And I do have a patent on this. I received a patent, I believe it was 2018 timeframe. And there's the patent number that's listed here, U.S. patent. I filed it back in 2015, and then I finally received the patent a few years later. It's for an energy management system. And so what you see in this configuration of this transformer is that we have the AC input, okay, which is inputting your source current and source voltage, and the output drives a capacitor and resistor, and that's what we measure on our outputs here. So we're driving a real load with the capacitor, and then we see the coil arrangements, which sets up the convergence. And the convergence is very important because that's what you see in all these devices, okay? So what is behind this PCM resonator? And this was a diagram that Tom Bearden put up during his lecture, but his diagram didn't really show a lot of detail. It was mainly focused on what is known in science in optics. You know, this is really an optical effect, but here we are running at a very low frequency, okay? We're not running at optical levels here. And so Tom didn't present all this detail that I'm providing to you today, okay? And so on the left side here, with waveform 3 and 4, is that you see the time reversed scalar wave component, okay, the transverse wave function. And it's time reverse, meaning that the wave is moving backwards in time, okay? And that's really the product of what we see here with wave 1 and wave 2, okay, are pump waves. And so the pump wave is producing wave 3, okay? That's our input into this device. And then we see a magnified output, which is wave 4, okay? Now also what's occurring here is that the device is producing this time reversed longitudinal output as well, okay? This is our second scalar component that I spoke about earlier, that W5. And this is what's going on in these type of devices, is that they lose weight as well. So if you took this device, you put it on a balance beam, you'll see that the balance beam will move. The device will get lighter, okay, because it's operating in this time reversed fashion. And this is really set up with two converging electromagnetic waves, okay? And so this is some of the mathematics here. W5 is, of course, a change in time, okay, which is anti-gravitic in this case. Okay, the next slide. PCM resonators, the output wave function. And so this is what we see here. The input wave function, W3, is your sine squared, and that's your pump waves, okay? And then they produce this magnified W4 term here, which is your output sine squared term. Okay, this is your outputs. This is what you see on oscilloscopes. Okay, this is for real. Okay, there's nothing here that's really made up. I mean, these technologies have been measured, and so this is for real. And so you see this time reversed output on the sine squared term here. Okay, so well, let's go back in history here. What exactly did Nikola Tesla do to make his magnifying generator? Well, he sets up this magnetic motive convergence, okay, with two coils, and his two coils are labeled M on his patent. So you can look up his patent and then see that he has two coils, two output coils, two capacitors, and a transformer coil arrangement here. And of course, he filed this back in 1896. So he's been doing scalar projects for a very long time here. Okay, but nobody understands it. No one, a physicist, you put this on a physicist's desk, he's going to look at it and says, well, we're going to change things around a little bit, put one coil. He's really talking about one coil arrangement, one capacitor operating as a resonator. No, that's not what Tesla was doing. Okay, he's setting up his convergence. Okay, so this is what Tesla was doing, okay, to get his convergence going here. He's got his generator, his two coils labeled M, and he's setting up his magnetomotive convergence here. And it's set up as mu times H, okay? And so that produces an output voltage, okay, with minimum current driving his transformers, okay? Now let's look at another device here. Another inventor came along, 1992, by the name of Stanley Meyer. He's on the internet. I believe his patent is also on the internet as well. You can download his entire patent. And this has been replicated and tested by another inventor. And he presented his information at the Tesla Tech conference a number of years ago, 5 or 6 years ago. And he replicated all of Stanley Meyer's equipment here, and he observed an efficiency because Stanley was able to tune his coils. Okay, he was able to tune his coils. He observed an efficiency of about 1,200%. Okay, and that's what was driving his output. His output is, you'll see number 71 and 61, and that drove a water, what Stanley called a water capacitor. Okay, and all that this water capacitor is just a couple of plates and water that he used, distilled water in his capacitor. Okay, so his dielectric in this case is going to be water. And so Stanley was producing a water fuel from this. Now, who was doing this before Stanley? Another inventor that goes by the name Yule Brown. Okay, and you can look him up as well. Yule Brown was producing what's called Brown's gas. And what is Brown's gas? It's a hydrogen-oxygen combination. Okay, normally when you disassociate water, you break it up into separate containers here of hydrogen and oxygen. Okay, but that's not what Stanley was doing here. And Yule Brown wasn't doing this either. Okay, he was doing this as well, setting up his water capacitor. And he was producing this gas called HHO. Okay, HHO. And we'll get into that a little later here as well. So this is what Stanley was doing. Okay, this is his device. I put the dots and the arrows here to show you how things are converging. He's setting up his resonant charge, what Stanley called his resonant charging chokes, okay, on his output transformer. So he had an input side here feeding these two resonant charging chokes, okay, and that's what drove his water capacitor. Okay, so what is this water fuel that Yule Brown produced, as well as Stanley Myers in his water car? Okay, because what Stanley did is that he took this apparatus and put it into a dune buggy, and you see that on the internet as well. And he ran his dune buggy on this water. Okay, so what is this? Well, it's known as hydroxy gas. That's what researchers call this. It's a special gas that's a combination of HHO. Okay, and a researcher a few years ago gave a very nice talk about this. It's electrically expanded water. Okay, electrically expanded water. And it's highly flammable. Okay, so this gas, it's a highly flammable mixture. And again, I want to emphasize that we're not separating hydrogen and water into two different tanks. It's combined as one. And so when you burn this gas, it burns cold. It doesn't burn hot. This gas burns cold. So it burns at a temperature of 266 degrees Fahrenheit or 130 degrees Celsius. Okay? So this gas burns cold. But here's the amazing thing about it. It can vaporize tungsten. And tungsten won't melt until you reach about 10,000 degrees Fahrenheit. Okay? But it can vaporize tungsten. Well, how can it do that? How can this gas burning cold, okay, vaporize tungsten? Well, it's electric. It's an electric flame is what that is. Okay? So you're made. So we have a multi-plate electrolyzer and a DC voltage and current. And that's exactly what Stanley was doing. Okay? And so the objective here, well, what's the objective of all this? Well, burn water, not gasoline. Okay? Burn water, not gasoline. And so Maury Keek came along. You can get his book, The Key to New Energy. Okay? And there's the ISBN number. You can get his book where he talks all about this water fuel. Okay, all these characteristics behind this technology. Okay, so we don't have to burn these hydrocarbons. We don't have to do this. We could just burn water instead. Run our engines on water. So what is this water fuel? How do you make it? Well, I bought one of these devices. Okay, you can see the plates here, a power supply. Now, the problem with this particular setup is that it's not efficient. Okay, it takes a lot of power to make this gas. And that's where the scalar energy technology comes into play, because you can replace that power supply that you see on on this slide here with a scalar energy generator, which is using either my transformer or these coils set up in this converging method like Stanley Myers did, or you can use a Tesla coil arrangement, okay, to make this gas. And what you do is that you pour your fluid, okay, you can use distilled water, okay, with the scalar energy, and fill up this tank and then make this gas with it, okay? So you can actually buy this, this water torch, okay? It's available online that makes this HHO. And the issue with this is that it's not energy efficient, okay? And you have to use a potassium hydroxide added to the water as a catalyst, okay? But Stanley mentioned that you don't have to use this catalyst. If you use scalar technology, okay, with this, replace that DC power supply with your scalar power supply and produce the gas that way, you don't have to use a catalyst at all. You can use straight distilled water with this, okay? And so your output is what? Water vapor, right? When you burn that gas, hydroxy gas, your waste product is water, which I think is quite fascinating. Okay, so this video, I highly recommend people to watch this video because it goes into quite a bit of background here on relativistic quantum field theory. And so when I saw this video, towards the end of it, I'm looking at it and I say, well, there's the scalar term, the F minimum. See, to produce particles with mass. Okay, you have two types of particles here. You have particles with mass and particles with no mass. You know, for example, a massless particle might be a photon or something. Okay, on that order. There's no mass associated with that. But yet, with particles like an electron, real matter, okay, has this output. And I looked at that and I says, oh my God, that's a scalar term. Okay, that's really producing a scalar wave. And so that's what mass does. It produces a scalar wave, which in turn produces a gravitational wave. A longitudinal wave comes out of this. And so it fits in what Tom Bearden spoke about back then, that matter is made of trapped electromagnetic energy. Okay? And so what you have are like two photons rotating, trapped, and producing the scalar wave component. And that's what gives you gravity. Okay? A very weak force. It's very weak, but it's not zero. Okay? I just want to emphasize that it's not zero. Okay, so this is my test bench. This is a scalar wave test bench. And it shows an oscilloscope, a power supply, my transformer, driving the resonator here, which is a capacitor and a load output, and some meters hooked up to it to measure the current and the voltage. And so I wrote some software that does all these calculations, okay, that determines what is my efficiency of this device, okay? And so with this power supply, it just generates my AC form, my sine wave, driving a transformer, because you can only power transformers, in this case, from an oscillating source. whether it's AC or a DC source. It has to be pulsed, okay, which of course is what Stanley Myers was doing here with this rectifier in his transformer arrangement. Okay, so you have this pulsed output, oscillating output, and so I wrote this software that reads the voltages and currents going into it, coming out of it, looking at the scalar wave component on this oscilloscope. And you see the actual scalar wave, the sine squared term, is the top trace. And that top trace is added to the sines, to the input sine current. Okay, so it's sines plus the sine squared term. And that's why you see this kind of funny looking shape at the top. And I'll go into a little detail in a few other slides here with that. So this is the real thing producing the real sine squared term. Okay, and that's what gets added into the waveform. Okay, so what are these waveforms? So I did some MathCAD waveform calculations. You know, I set this up in MathCAD, put my equations in, and so I see what the input waveform is. Okay, that's my sine wave input. And the scalar waveform on the output, okay, is up there at the top. That's my sine squared term. And so when these two waves are added, which is what you see that kind of funny shape there at the bottom, the summation of the input and scalar waveforms. This is what you actually see on your scope. And so to go back a slide, okay, there's your oscilloscope, and that's that funny wave shape there at the top, that blue wave shape. Okay, so this is what happens when you add these two together. And so the actual scope is what we see, okay? This is input waveform, the sine wave, plus the sine squared term, okay? And that's our scalar wave. And so this is an actual scope reading. So what are we doing here? Okay, to determine transformer efficiency using AC circuit analysis, this is what we're actually doing. So we have our AC waveform on the input, and we're looking at voltage and input current. On the output, we're seeing our output current and our load. And so the device under test is our PCM. And that's where we have our coil capacitor arrangement, okay? And so how do we measure AC circuit analysis? Well, we look at these various values here, and then we look at the phase shift, okay, the apparent power versus the real power, and that's where we see the reactive power, okay, on our technology. So this is just plugging in some test values here, and this is what we see, power input and power output, okay? And then from that, we can determine the efficiency. And this is what my software does. It does all these calculations here. Okay, so the next slide. This is my software. This is written in Visual Basic, actually. Visual Basic is actually a very solid platform to write this software. And so it reads the scope, sends messages back and forth to the scope, and takes all these readings on the input and output and does these calculations of computing the efficiency and input phase angles and output phase angles. So it's doing all this number crunching, okay? And then we see on the output of this thing is that, oh boy, 90% efficient. And usually transformers are right around 80%. So we're seeing an increase in efficiency on this output here. So that's how we know that the output of this device is that it's time reversed. There's some time reversal going on here. Okay. And so what is my software doing here? Well, it's doing all these calculations. Okay. So it's looking at phase angles, apparent power, reactive power, taking the arc cosine, and doing all this number crunching. Okay. Now, this software is actually available to be downloaded for free. Okay, it's on my website. And it works with this particular type of scope that we have, that I use. It's a Tektronix 2024B scope. And I think they're actually, they're still available, I think from Newark Electronics would be the supplier on that. And so I captured all these screens from the transformer here, and it's doing all these number crunching algorithms here. So I'm able to capture these screens and then load them onto the clipboard and make up these slides here. Okay, so Tom Bearden's applications for this device. And Tom spoke about scalar wave interferometry. Okay, Tom wanted to get a big DARPA military contract. So he never really went into a whole lot of detail on his device, what he was actually doing, but he did present a lot of this data. Okay, and so I had to spend a lot of time putting all this together. All right, putting all this together because Tom wanted a big DARPA contract, okay, to do scalar wave interferometry. And what is scalar wave interferometry? Well, it's a defense application. It requires two ground-based scalar wave emitters, okay? And these two emitters, where the beams cross, is your target. Now, it could be an airplane, a satellite, whatever, okay? But where these beams cross, create a strong electromagnetic field, okay? And it can destroy electronics in your target zone. So the next slide here, scalar wave interferometry. I did a lot of mathematical analysis with scalar waves. And I noticed that, you can create an electromagnetic virtual ground where these beams cross. Wow, that's cool. And then when you look over to the right side of this, if you phase adjust your scalar wave terms here, you just shift them, okay? It says, you can create a strong AC potential, okay? Right there in space. So you can short out anything, okay? Anything that's there, you can short it right out. Because in that region of space is creating a strong electromagnetic AC potential. Wow. So this is what Tom was speaking about in the conference, okay? And so scalar wave interferometry, okay? You have your two scalar wave emitters, okay? And that's where you can create either a virtual ground or a strong AC potential, okay? So these are all visuals here. Tom did show something like this in his lectures, okay? He did speak about these interference patterns, okay, of scalar wave interferometry. Okay, so this brings up another researcher that I ran across. Back around a while ago, I would say about a good 10 years ago or so. a researcher by the name of David Sereda made a movie. And in this movie, he interviewed this researcher, this developer at Lockheed Skunk Works, I believe. I believe it's Skunk Works. Boyd Bushman is a weapons developer. And he did this experiment, and he spoke to David about it, giving him all the details of this experiment. And you can actually replicate this experiment, and I'm going to present all this data here that I have of what Boyd did, what Boyd Bushman did. And what he did was that he took two magnets, which is really our technology, okay, because we set up these converging magnetomotive forces, which are really two magnets, and you force them together. And when you take these magnets and you force them together, it decreases the mass acceleration effect, okay? It generates a time-reversed effect here, and it's anti-gravitational, okay? Basically the same thing what we're doing in our technology, Boyd is doing with actual magnets. And you can do this. You can do this experiment. So what did he do? Well, this is the experiment that I did. I conducted this back in 2009. It's called the Boyd Bushman drop test experiment, where you take these magnets, you kind of wrap them up to look like a rock, and you drop them, okay? And then you observe the test rock with an increased mass acceleration effect, okay, with the test rock, with your test rock. And so here we have it. You know, this is how you make the device. Okay, you have two neodymium magnets. And what you do is you set up this jig here to force them together. And you actually epoxy them. You can use JB Weld epoxy on these magnets. Okay. And there's the jig there, forcing the magnets together. And there's the magnet assembly. You notice in this case here, the north-north configuration is together. And it doesn't really matter. It could be south-south or north-north, this configuration here. And there's your magnet assembly, showing them epoxied together. There's an ordinary rock. There's lots of rocks there in Arizona where I did this test. And then you take the rock, you just wrap it up with some electrical tape here and a nice bright blue rock here, and then some red electrical tape, for example, on the right. And then what I did was extend Boyd Bushman's experiment using magnets in a attractive configuration. Okay, and I compared that as well. So that when I did the experiment here, comparing the rock dropped with the rocks with the opposing configuration, fell slower, replicating Boyd Bushman's experiment, because he did this at Lockheed, okay, and I observed the same effect, okay, the same effect, and you can replicate this as well, and I videotaped it, okay, and you can actually see the rocks with the opposing configuration fall slower, but the rock with the magnets in the attractive configuration fell faster. I said, aha, that's interesting, very interesting. Because when you show these rocks in the attractive configuration and the opposing configuration, guess what? You can build a warp drive with this, okay? Because magnets they bend space-time. They not only produce their magnetic field, but they also bend space-time, so you can build an Alcubierre warp drive using these magnets, okay, and these various configurations. And this is how you do it, okay? And so I came up with what's called the ABBA warp drive engine propulsion technology, okay, where you see magnets in the attractive configuration and then magnets in the opposing configuration, and you spin them. And when you spin them, you get something called the Barnett effect, okay? And then when you spin them in counter-rotating fashion here, you can get a counter-rotating setup here that eliminates what's called the P factor. And that's what you observed in engines, okay, plane engines, is that you have to rotate these propellers in opposing configuration to keep them from spinning the whole craft. So that's where this dual nacelle configuration comes into play, okay? Because you have magnets spinning in there, and you must spin in such a configuration where it counters the P factor effect, okay? So you can look this up as well. So this is how you build a warp drive engine, okay? And it's called the Alek Bushman Alcubierre warp drive engine. So it's just a silly little name I came up with there, okay? So I'm not opposed to gravity, okay, but our technology is. So this is a cute little t-shirt I came up with. And this is my business card with my email address and website. So you can check out the website, goes into a lot more detail. You can look at it, ponder it. This technology, see how you can replicate some of this. Okay.
Thank you, Bill.
And these are all my references.
Right.
Right here. And so that's my presentation.
Great.
So
Thank you, Bill.
Okay, very good.